In this video, I'll be solving this exam. I believe it's an actual exam, or if not, it's a practice exam, final exam that was given at UCLA for its Math 31B course, the course about integrals, exponential logarithm functions, the integration techniques, and infinite series. Okay, and Taylor series, Maclaurin series. That's what it usually ends in. Okay, so there's some good problems in this exam, practice exam or actual exam. So this is a good video to watch and get some practice problems from if you're here studying for the class, whether you have this actual teacher or not. I don't know who this teacher is, but I was able to find this exam online. Okay, and one more thing, the last time I did this, there's a lot of comments from a lot of people that were complaining how easy these problems were. In the last video, at least, not in this one. This one, the level is a little more challenging for some of them. Just a disclaimer, I'm not the one writing the questions, okay? I'm just here to solve it, to help you out if you're a student there. Or if you're just watching this and you're taking a similar class, okay? So don't blame me for easy problems. Blame the teachers, the instructors that wrote these problem sets or this exam. All right, if you find this one too easy or too hard, blame the teacher. Don't blame me for it. I'm just here to solve them and help you out. All right, with that said, let's begin. As always, you should scan the problem set, if this were an exam, to see which one is easiest to solve first. And you should just begin there. Pick up the easy points first. So that's what I'm actually going to do. Okay, so if we scan through the test, all right, these are strange multiple choice problems that I'm going to skip. This one is some weird matching for Maclaurin series. I'm going to skip this. Limits, I'll probably do this first. Okay, so you should be scanning the exam first before you even begin problem number one, because problem number one actually might take some time. Okay, so, but for the purpose of this video, I'm going to go in order. So just for simplicity, that I can keep track of which problems I did already. All right, so with that said, let's begin with number one. So this is a multiple choice. Select the correct choice in each of the following questions. No justification is required. So I pre-solved all these questions, as you can probably see, in the interest of time and to make sure that I got most of them accurate. But do check my work and my answers, because there was no answer key that I found. I did check some of them with like Wolfram Alpha to be sure I was correct, but some of them there's no answer. So double check my work, please. All right. So this is asking this series is convergent if which of these choices are true. So let's go through the multiple choice. So first of all, we can break this up as summation as n goes from 0 to infinity, a sub n, plus summation as n goes from 0 to infinity, b sub n. So each individual one should converge as well. Okay, let's go through the choices. Limit as n goes to infinity, a sub n plus b sub n equals 0. If this is true, does that mean the series will converge? For sure not, because what if an and bn are the harmonic series? It doesn't say that an and bn are different, but if they are the same and they're both the harmonic series, for sure the limit, so let's say is 1 over n, and let's make a different harmonic series, 2 over n, these are both harmonic series. This limit would for sure be 0, but then we know the harmonic series diverges, so clearly it's not choice 1. An converges to 0, and bn diverges. Well, if one of them diverges, the whole thing diverges. So no, that's not true. And if one diverges to plus infinity, the other diverges to minus infinity. No, that's not true. It doesn't work like that. Infinity minus infinity, remember, it's indeterminate. So not always true. So we cross that out. An and bn are conditionally convergent. It seems to be true. Let's hold that off. Well, for 5, we can already cross it out because 1 was not correct. So by process of elimination, it's 4. The confusing part of this choice is, why does it say conditionally convergent? Well, if it's absolutely convergent, remember that's if the absolute value of the series converges. But we don't care about that. We care about the original guy, which is what conditional convergence is. If the absolute value doesn't converge, but the original guy does, it's conditionally convergent. So all we care about is the original guy. So you can imagine this conditionally convergent is just saying convergence. If they're both individually convergent, then it's totally fine, as I was saying earlier. Okay, so that's how we think through this problem, or that's how I would think through it. Next, the radius of convergence of this guy is, well, to find radius of convergence, you always use the ratio test. So we go through the motions, limit as n goes to infinity of, we replace each n with an n plus 1, and we multiply by the reciprocal. That's the procedure, okay? N plus 1 factorial divided by n factorial, that's just n plus 1. X to the n plus 1 divided by x to the m, you subtract the powers, you just get x to the first power. And similarly, you subtract the powers, you would get 2019 on the bottom. All right? We take the limit as n goes to infinity, it's infinite. So it never converges. This series diverges all the time. Okay? Can a radius be infinite? If it's infinite, like remember the Taylor series for e to x has an infinite radius of convergence, actually, if I remember it correctly. But that means it converges for all values of x. But we just said, by the ratio test, since this is not less than 1, it never converges. So how can the radius be infinite? It doesn't work, right? So we cross these two out. If the radius is 0, that means it only converges at the center, but we just said it never converges. Cross that out. It never converges, we just said, so cross this one out as well. Answer is 5. None of the above. It never converges. Let R be a real number. The sequence a sub n equals 1 over n to the r. Which one's true? Does the sequence diverge for r is greater than 0? So let's pick, for example, r equals 1. Does the sequence converge if we take the limit as n goes to infinity? It does. So it doesn't diverge. Cross that one out. Does it converge for all r is less than 0? So let's pick r is -1, for example. Okay, which means this is n, 1 over n to -1 is n. What happens if we take the limit as n goes to infinity? If this, it clearly diverges, so not convergence. Does it diverge to infinity when r is equal to -1? Well, we just did that example. So it does. So we keep that. Is it increasing for all r greater than 0? Well, this one, clearly, as n gets bigger, the value 1 over n gets smaller and it approaches 0. So not the true, and it's not none of the above because 3 is true. Okay? Which of the following is true about this series? Is it convergent, divergent, conditionally convergent, absolutely convergent, or you can't decide it, or none of the above? Okay. So, does this original guy converge or not, first of all? Okay? If we just do a simple comparison test, because sine of who cares is always between -1 and 1. Okay? And then we attach an alternating sign. It's still in between -1 and 1. So this guy is always less than 1 over this guy. Or I can even do the sum or the sequence. Doesn't matter. Okay? To be consistent, I'll match it there. But it's, as I just said, this guy is always less than 1 over n to the pi over 3. Okay? And even if there's no change in sign, this inequality holds as well, which is what I wrote actually. Okay? This guy is a p series where p is greater than 1. Pi is 3.14 or something, right? Divided by 3, that's clearly greater than 1. Okay, so it's convergent because p series converge when p is greater than 1. Okay? Since this is convergent, and this is even smaller than this, then this guy has to converge as well by the comparison test. Okay? So we already know that it should be conditionally convergent. It's for sure not divergent. Okay? And convergent divergent, this is clearly not number 3 either, because we just said it's convergence. Okay, now, is it 1 or 2 or is it 5 now? Why is it 4? Why did I circle this one? Is it conditionally convergent or absolutely convergent now? If we take the absolute value of this, well, the changing sign, the -1 to n would go away, but actually sine of n to the n also changes sign sometimes. Okay, so it's some value that's going to be less than 1 still. And we can use the exact same comparison test again. So it's going to be absolutely convergent. So choice 4. Hopefully that made sense over there. The key point was this comparison test over here. And to determine absolute convergence, you get rid of this changing sign, but sine of n to the n, it's itself going to change sign. Not every single term, but it will change sign sometimes. Okay? You don't know, but we can still make a comparison. Okay, this one, limit as n goes to infinity of n over n plus 1 to the 3n. If you go by the choices, they sometimes give you hints. Okay, maybe it's something to do with the limit definition of e is what I was thinking right away. And it is. And this should look familiar as well, actually. If you don't remember it, but if you look at choices, that might give you the hint as well. So what if I invert this and put it as a negative exponent and divide through by the n? This looks more familiar now, right? To the limit definition of e that you might have learned. So let's break this up into 1 plus 1 over n to the n power, and then the whole thing to the minus 3 power. Properties of exponents, I could do that. This is e, if I take the limit as n goes to infinity. It's continuous, so, sorry, it's not continuous, so this is the limit as n goes to infinity, but you can use that property of limits, where you can find the inside first, and then find the outside, right? Or plug it into the outside. So the answer is e to the minus 3 power. Answer is 3. Choice 3. So problem number 2 says to match these with one of these. You want to find the Maclaurin series or the Taylor series at 0 for these 3, and you got to pick from these. Okay? And then part D of this problem says find the second Taylor polynomial of this guy around 1. So let's go through this first. These are series similar to some series that you should have memorized. Okay? There's the e to the x Taylor series that you should memorize, sine x, cosine x, and then this basic one over here as well. 1 over 1 minus x. This is when you first learn power series. This is the Taylor series for it, or the Maclaurin series for it. Taylor series that x is equal to 0, I should say. Okay? Now, with this knowledge over here, we're going to make this, we're going to use this and make it look like this up here. How so? What's the difference? There's a 2 on top, and this is a 1 plus 4x cubed, okay? So what if this is the whole point of power series? They're like functions. Well, this is the function over here. So what if I replace x with minus 4x cubed? So I gotta do it on both sides, so that's what I did here, okay? And then I multiply by 2 on both sides. Now, this is exactly the same as this over here, okay? So that's over here. Now, just to get a matching answer over here, I gotta do some algebra. Okay, I did like 2 steps in one over here, but over here, I distribute this n power to both the minus 4 to the n and the x cubed. Okay, and then by properties of exponents, this becomes x to the 3n power, okay? And then this 2 comes from multiplying 2 on both sides. Okay? Now this, I broke this further up into minus 1 to the n, 4 to the n. Well, 4 is 2 squared, so again, I did 2 steps in one there. 4 is 2 squared. Okay? This I didn't touch. Now this 2 I can move inside. This is 2 to the first power, and this is 2 to the 2n power by properties of exponents. So by another property, the one where you add the powers, it'll be 2 to the 2n plus 1. Okay? And we find the matching choice. It should be choice 1. Okay? This one, you start with e to the x. That's the easiest one to memorize, probably. Okay? Replace x with minus 2x cubed. That's right there, right? So e to minus 2x cubed is, well, replace this x with minus 2x cubed as well. And then you just go through the motions of algebra. Again, distribute this n power to each of the 3 there. Minus 1 to the n, 2 to the n, x to the 3n. And then you should have a matching choice of 4. Okay? This one, start with cosine x. Okay, so cosine x is this. You just have to memorize that. Replace x with 2x cubed. And then go through the motions again. You will get this after the algebra. And then find the matching choice. It should be 8. Okay, I went kind of fast on that one. But you can, of course, pause the video and see my work if you need to. Okay? Now, to find the second Taylor polynomial, it probably means second degree Taylor polynomial of this guy around 1, we got to take derivatives up to the second derivative, up to the matching degree. So second degree means we take up to the second derivative. Okay? So if this is the function, we call it f. we need f prime and f double prime. So derivative of this is just e to x plus 2x plus 3. Okay, and then derivative of this is just e to x plus 2. For the Taylor series, it's centered at 1, so we need f of 1, f prime of 1, f double prime of 1. That's the whole point of taking all those derivatives. Okay, so I plug in 1 into these, I get these values over here. I won't go over that. Okay, so this is the formula for the Taylor's polynomial from 0 up to the second degree term 2. Okay, so when n is 0, we have the 0th derivative, which is e plus 3. X to 0 is 1, or so x minus 1 to 0 is 1 over 0 factorial, which is also 1. So we just left e plus 3 for the first term. N equals 1, we need the first derivative, which is e plus 5, x minus 1 to the first power over 1 factorial, which I didn't write because it's just dividing by 1. Next term and last term, n is 2, we need the second derivative, which is e plus 2, x minus 1 squared over 2 factorial, which is just 2. That's our answer. These are easy problems usually when you need to find Taylor polynomial. Okay. Now we're going to compute limits. It's all about L'Hopital's rule on this page. So we want limit as x approaches 1, ln of x to the ln x power. Well, if we do the usual of trying plugging in 1 first, we get 0 to the 0 power. This is indeterminate. So what do we do when we have indeterminate power? We got to log both sides. So we ln both sides. You can use any log, but ln is usually the easiest. ln y equals ln of ln to the ln x power. Lots of ln, so be careful with your notation. Write clearly, otherwise you might get confused. Okay, now we're going to use properties of logs to move this power out. So it'll be ln x times ln of ln x. Okay, and I rewrote it like this. Instead of ln x, I wrote it as divided by 1 over, or multiplying by ln x, I wrote it as dividing by 1 over ln x. Why do I want to do that though? Well, now if I take the limit of this, it's infinity over infinity. So now we can use L'Hopital's rule. We can only use L'Hopital's rule when it's 0 over 0 or infinity over infinity. It has to be an indeterminate quotient. Okay? Differentiate the top, we need a chain rule. It'll be 1 over ln x times 1 over x. We need a chain rule here as well. This is like ln x to the negative 1 power, so use the power rule first, and then derivative of the inside. Clearly the 1 over x would cancel. Okay? Now I move the minus sign out, and then I move this to the top. Negative exponent, I can move it to the top. So it'll be ln x quantity squared over ln x. Okay? Which simplifies to ln x clearly. And then the limit, after we go through the simplification, is 0. But you're not done yet. We found the limit of ln y. We want the limit of y. So what do? We got to exponentiate that. So we just take this limit and then exponentiate it. So e to the 0, 0 comes from there, is 1. And that's your answer. Okay. Next one, limit as x approaches 0, cosine of x to the 1 over x squared power. If we plug in 0, you would get like 1 to the infinity, which is indeterminate again. So we use the same technique. We log both sides. Okay, and we use the property of logs, where you can move that power out in front. Now this, if we take the limit as x approaches 0, same limit over there, it's 0 over 0, so we can use L'Hopital's rule. The top, we would need chain rule. So it's 1 over cosine x times minus sine x. This is just power on the bottom. Okay? The top we can simplify to minus tangent x over 2x. Okay? This is still 0 over 0, so we can use L'Hopital's rule again. Differentiate the top, we would get minus secant squared x. Differentiate the bottom, we get 2. So now we take the limit, it'll be 1 on top with a negative sign, and 2 on the bottom. So minus half is the limit of ln y. We want the limit of y though, so we exponentiate again. So take this, put it as the power of e. That's the answer. All right, last one on this page for L'Hopital's rule. Limit as x approaches 0, 1 over sine x minus 1 over x. This is infinity minus infinity, so we can't use L'Hopital's rule directly, but we can, when it's like this, indeterminate difference, we can just make one fraction, and then usually we can use L'Hopital's rule after that. So we need a common denominator. So that's this motion over here. Okay. and then I combined to one fraction. Now it's 0 over 0. So now we can use L'Hopital's rule. Derivative of x is 1, derivative of sine is cosine. Derivative of this, we need product rule will be first, d second, plus second, d first. So that's that over there. I'm not going to go through it. It's still 0 over 0 though if I plug in x is 0, because 1 minus cosine 0 is cosine 0 is 1, so 1 minus 1 is 0. The bottom we get 0 plus 0, so still 0 over 0. We got to use L'Hopital's again. To differentiate the top, you would just get sine x. Differentiate the bottom, you need the product rule for this one again, so be careful. Okay, and then derivative of the sine is cosine. Okay, now we plug in x is 0, we get 0 on top, and then 0 plus 1, which is 0. And that's your answer. The limit is 0. Here you're asked to find the interval of convergence of this power series. It's a very typical procedure. To find the interval of convergence, you first need the radius of convergence. And to find the radius of convergence, you use the ratio test. Okay? So we go through the motions of the ratio test. Limit as n goes to infinity. Wherever there's an n, put n plus 1. And then multiply by the reciprocal of this guy. That's, if you remember the formula, it's limit as n goes to infinity of a sub n plus 1 over a sub n. So that's why you put n plus 1 as is, and then flip it and multiply. Multiply by the reciprocal. Divide by a sub n. It's the same thing as that. Okay? We go through the motions of simplifying. You can subtract the powers. So n plus 1 minus n is just 1. So 3x plus 4 to the first power. N and n plus 1, we can't really simplify that, so we leave that there. But 2 to the n, divide by 2 to n plus 1. You subtract the powers. You get 2 to the minus 1, which is 2 on the bottom. Okay? These don't depend on n, so I can pull it out of the limit to focus on calculating the limit, this limit over here. What's this limit? It's 1. The same degree, take the ratio of the leading coefficients for like a rational like function, okay? So this limit is 1. And therefore, your limit of the original guy is, you still have this guy over here, right? So it'll be absolute value 3x plus 4 over 2. So you can't drop the absolute value sign even when you pull it out, by the way. Hopefully you know that. To find the radius of convergence, the ratio test is the convergence when that result is less than 1. Okay? So the radius of convergence, you just multiply 2 on both sides. 3x plus 4 is less than 2. This is the radius of convergence. Sorry, that's not the radius of convergence at all. Ignore that's the radius of convergence. But this is the right procedure, though. Okay? So, okay, let's backtrack then, since hopefully I didn't confuse you. But the ratio test says that this series converges when that limit is less than 1, okay? Now, to find interval of convergence, you got to find all values of x. So you got to solve this inequality, basically. So multiply 2 on both sides. And then here, to break this inequality up, you keep it as is for one side. The other side, you flip the inequality. So instead of less than, it's greater than, and you put a minus sign here. So greater than negative 2, or you can write it like this, okay? And then you go through the motions of solving for x, so minus 4 everywhere, and then divide by 3. You should get this, okay? So you can see from here the radius of convergence is not 2. So I messed up there. But luckily it didn't ask for radius of convergence. So we're almost there. We got to check the endpoints for the interval of convergence. Okay, why do we need to do that? Remember, the ratio test says that when it's equal to 1, when that limit is equal to 1, it's inconclusive. So at these two endpoints here, it's equal 1. So we got to check them manually. And usually it's not too hard. So x is negative 2. Let's check that. We plug in x is negative 2 back into here. Okay, so that we get minus 6 plus 4 to the n over n times 2 to the n. This is minus 2 to the n, which we can break up as minus 1 to the n times 2 to the n. Okay, the 2 to the n's cancel. We are left with minus 1 to the n over n. This is clearly convergent. This is the alternating harmonic series. Okay? Similarly, the other endpoint, when x is minus 2/3, we plug that in back into the original guy. We would get minus 2 plus 4 to the n over n times 2 to the n. Okay, simplify. This is 2 to the n. They cancel, so you're left with 1 over n. This is clearly divergent because this is the harmonic series. So we want to include this one, but not include this one. So we change up that inequality to this. We put equal sign on that side, but not on this side. And if you want interval notation, it's -2 with a square bracket, but 2/3 with parentheses. Either one should be fine. Okay? Integrals, these aren't bad at all, actually. We want to evaluate the integral of 1 to e ln of x quantity squared dx. So how would you approach this if you didn't see any of this? So this is why you should try the problems first on your own. So my bad that I didn't show you it first, but in the interest of time, I wanted to work them all out. So from experience, hopefully, you know that to find the integral of ln x, you have to use integration by parts. So that's my hunch, that we might need to use integration by parts here. Like, I don't see, this is clearly not a trig integral. I don't see any trig sub that I can do. It's not a rational function, so I can't use partial fraction decomposition. Can I make a substitution? I don't see any obvious one. So, are we out of ideas? Well, we can try integration by parts. Just, again, from experience, we know that if it's just ln x, we need integration by parts anyway. So let's try. What if we let u be ln of x quantity squared? Du is, well, we need to chain rule, so it'll be 2 times ln x times 1 over x times dx. Okay, dv is whatever is left, so the only thing left is dx. So v is equal to x, okay? Integration by parts is uv minus v du, so it'll be x ln of x quantity squared. Evaluate from 1 to e, minus v du, so 2 from there, integral 1 to e. 1 over x times x is just 1, so you're left with this ln x dx. Okay? And here, as I just said, we need integration by parts to evaluate if you don't remember this integral. Which I don't think you need to, but of course it's helpful to. I think it's x ln x minus x or something like that. Yeah, it is. But just use integration by parts again if you don't remember that integral. Okay? So u is ln x, du is 1 over x dx, dv is dx, v is x. Okay, so again, uv minus v du. So just be careful with parentheses. So this integral, we're going to replace with the uv minus v du, but it's being multiplied by the 2, so we need parentheses. So it'll be x ln x from 1 to e minus integral of what's x times 1 over x, that's just 1, so 1 dx. Okay, now let's evaluate this integral. That's easy, it's just x. And then usually I evaluate everything at the end together from 1 to e. Okay, so it's a little messy notation there, but I just evaluate everything at the end. Okay, plug in the upper bound, minus plug in the lower bound. You can check my work. This I checked on Wolfram Alpha. This is correct. It's e minus 2. That's the final answer. Okay, next one, improper integral from 0 to infinity, x e to the minus x dx. This is a clear integration by parts for sure. So hopefully, from experience, you can tell that right away. All right. Now, I don't know how picky your teacher will be, but the proper way technically to do this is we need to change this infinite limit to a limit. So you write it like this first. Okay. And then here you use the integration by parts, use the tabular method if you want, or I just did it as usual here. U is x, du is dx because we want to reduce the power. dv is e to the minus x dx, dv is whatever is left. V is e minus e to the minus x. uv minus v du, that's this right there, okay? Integral of e to the minus x dx, that's just minus e to the minus x, okay? And then, like in the other problem, I evaluate everything at the end. Okay, so that's this step here. Now we have to take the limit of this, okay? How do we take the limit of this? So that's what I did on the side over here, without the minus sign. This is infinity times 0. So we got to make it infinity over infinity or 0 over 0. So why don't I just change this negative exponent into a positive exponent like that. Now it's infinity over infinity. So I can use L'Hopital's rule. And if I take the limit, that's 0. Okay, so this guy is 0. This guy, if t approaches infinity, this guy approaches 0 as well. If t approaches infinity, this is a constant, so it's 1. So the final answer is 1. Okay? Last one on this page. We have this integral of this rational function. So immediately I thought, let me do long division. So that's this process over here. I'm not going to go over it in the interest of time. You can see my work if that helps. So this is the quotient, and this is the remainder. So the remainder still goes over the divisor. Okay? Now this is much easier to integrate. Well, these two are for sure easy to integrate, right? This is just power rule, this is just power rule as well. This one we can use partial fraction decomposition. That's the step over here. This bottom I can factor as x plus 3 times x minus 2. So the two partial fractions are like this. A over x plus 3 plus b over x minus 2. Multiply both sides by the two factors, x plus 3, x minus 2. The left-hand side, you're left with minus 6x plus 1. This side, you're left with a times x minus 2 plus b times x plus 3. For this type of partial fraction decomposition, remember that if you see my other videos, the quick way to do it is we plug in nice values of x. When x is 2, this goes away. We get minus 11 is 5b, so b is minus 11 over 5. When we plug in x is minus 3, this is a nice value because this term goes away. And then we can find that a is minus 19 over 5. Okay, so we replace a and b as the coefficients, and then I move that all over here as well. Okay, this is the partial fraction decomposition. Okay, now these are easy because these are logs. Okay, so this one is x cubed over 3. This one is just 6x when we integrate. This is minus 19 over 5 ln of x plus 3. Don't forget your absolute values though. And this one is minus 11 over 5 ln of x minus 2 plus c, and that's your answer. So I wouldn't bother simplifying here in the interest of time on your time test. If you have extra time, then you can by all means try to simplify, but I feel like this is good enough. Number 6, find the Taylor series of 1 minus x to the minus 2 power around 0, so centered at 0. Hint, differentiate the Taylor series of this around 0. Okay? So how did I do this? Well, I took the hint. I started with this series, which is one of the ones that you should remember. As I said in the, I think problem 2 or something like that. 1 over 1 minus x is summation as n goes from 0 to infinity of x to n. This is just the geometric series, remember. Okay? We can differentiate power series. So we differentiate both sides. Okay, this one, we just use the power rule and the chain rule. Okay, be careful you need the chain rule. I almost forgot it. So I got some weird answer later. And then here we can differentiate. If you remember from lecture or something, the order doesn't matter if you differentiate or sum, something like that, right? So we just use the power rule here. Instead of some number, it's some variable n. It's just n x to n minus 1. When n is 0, the first term would be 0, so you can just start it from n is 1. Okay, you can start from n is 0 as well, but the first term is 0, so usually people just start from n is 1. Okay? Now, after simplifying over here, you would get this. Okay? So that's the answer for part A. Part B, evaluate this infinite sum. How in the world would you do this if you didn't find this in part A? This is not one of like the special series that you really were asked to memorize. So you just have to be smart about this. This is a test. This is a related problem probably. This is problem 6, part A, part B. You probably need to use this. Okay? It has to be something that you are able to find, essentially, on this exam. So you got to think outside of the box. Okay, so we're going to use this, basically, since I already thought through it for you. Hopefully you were able to think through it first for yourself. To get this to look like this, how can I do that? Well, the x seems to have to be like 2, right? But this is not in a fraction. So we can just move this as a negative exponent. Okay? So, what did I do? First of all. Okay. So, what did I do again? Okay. So, 2 to the n on the bottom, we can rewrite as half to the n power. Why do I want to do that? Well, because I need this to be like n minus 1 power. The n's are matching. I'm assuming my x is 2½ now, right? But this is the n, that's the n minus 1. So how can I make there to be a minus 1 there? Well, if I multiply by half to the negative 1 power, I can combine these two by properties of exponents, right? It'll be n minus 1. But I can't just blindly multiply this. technically this is multiplied by 2, right? I can't just randomly tack it on. I need to get rid of it. So to get rid of it, I multiply also by half, because half to the negative 1 power times half is back to 1. Okay, so multiply by 1, you can do that to anything, right? It doesn't change anything. So that's the little trick here. Now this half, I can move out to the front of the summation. It's a constant. And now, as I said earlier, we can combine these by properties of exponents, okay? Now this looks exactly like this, except x is half. Okay, that's the key point for this problem. Since this guy is this we found earlier, if x is half, then plug in x is half equals, we can plug in x is half on both sides. So this is on the left-hand side. This is on the right-hand side. So 1 minus half to the minus 2 power. Okay, and that is half to the negative 2 power, which is 2 squared, which is 4, okay? So this guy is equal to 4. Okay? This guy is this right here. So this guy, which is this guy, right, is half times this guy, which we just said is 4. So half times 4 is 2. So this is putting all the pieces together. Okay, hopefully that made sense once again. You only really know how to find the infinite sum of, like, if it's a telescoping series or it's the geometric series or one of the Taylor series that you probably know really well, like e to the x, sine x, cosine x, but it doesn't look like any of those. So how in the world would you be able to find it? Well, this one looks kind of close to this. So if you had gotten part A correct, then this one is not too bad to solve if you have pieced the pieces together like that, connected the dots. All right. Now over here, consider g of x as this guy. Find the 50th derivative at 0. For some reason, UCLA loves to ask these type of problems. So you got to know this, it seems like, at this school, for this course. Okay, so again, we're going to use the power series representation that we found earlier. Okay, so it's all banking on that you got part A correct. Okay, so I don't know how the partial credit would work if you didn't get part A correct, but anyway. This is x to the 10th power times this, is it not? So we can multiply both sides by x to the 10th. That's what I did right there. Okay? This is the power series representation of 1 over 1 minus x quantity squared. Okay? Now this x to the 10th, I can move inside the summation and use properties of exponents. Okay, so it becomes n minus 1 plus 10, which is n plus 9. Okay? So if I expand this out, just to help you guys visualize, I don't really need to do it, but to help you out, it kind of helps me at times too if I'm rusty on this. Expand out term by term. X to the 10th plus 2x to the 11th, that's when n is 2. N is 3, is 3x to the 12th. N is 4, 4x to the 13, so on and so forth. Why did I write this one in particular? Well, when x is 41, you would get 41x to the 50th, okay? So what happens when you start taking derivatives of power series? This is the whole trick for a power series. When, for example, g of 0, this is the center of the power series, by the way. When you evaluate derivatives at that center, things disappear. So for example, g of 0, if you look at the power series representation, everything would be 0, because 0 to what, who cares what power is 0? Okay? If you take the first derivative, you would have 10x to the 9th plus 22x to the 10th, so on and so forth. Plug in 0, everything's still 0. Let's take to the 10th derivative, so you can just imagine we keep using power rule. So it'll be 10x to the 9th, and then bring down the 9 next time to the 8th, bring down the 8 next time to the 7th, bring down the 7 next time. So you notice that there's a 10 factorial that's happening. So when you take the 10th derivative, this x to the 10th will eventually be x to the 0 power after you take 10 derivatives, which is 1. So you're left with 10 factorial. And then everything else still has an x. When you plug in the center, x is 0, they would go away. That's the whole point of these power series, if you didn't realize. Okay, so the 50th derivative, by the time you take 50 derivatives, all these would have zeroed already. Okay? Now this one, if you take 50 derivatives, then you're left this term with x to the 0 power, which is 1. So you're still left with this constant of 41. But when you did the power rule 50 times, you have 50 factorial. And that's your answer right there. So these are a piece of cake, actually, if you just know the simple concept. Okay, so to review one more time, this power series representation is nice when you plug in values of x when you plug in x as the center, because things cancel. Okay, so when you differentiate many times, you keep using the power rule, so you'll have that factorial somewhere. Okay, and then when you take 50 derivatives, all the earlier terms would go away. For example, when you have like x squared, you can only take like 2 derivatives, right? A 3, and then before it goes to 0 is what I'm saying. Because x squared would be, first derivative is 2x, second derivative is 2, by the third one, it's 0. Okay, so everything before the 50th degree term would have zeroed already when you take 50 derivatives, okay? So you only really care about this 50th degree term. Everything after, who cares? There's x to some power, you plug in x as 0, it would be 0, it would go away. So you only really care about this term here. That's why I wrote it out. Now, you still have this 41 coefficient, but when you do the power rule 50 times, you would have 50 factorial. And when you differentiate 50 times, this would be x to the 0 power, which is 1. So times 1, which I didn't write. So this is your answer. Okay, again, I've seen very similar problems of this type in a lot of UCLA exams, so you gotta know this. So problem 7 is asking about convergence of series, and there's the whack problem on this page. So I'll get to it when we're on B, okay? This one asks if they're conditionally convergent, converge absolutely, conditionally, or not at all. In case they converge absolutely, find the limit of the series. I'm assuming they're asking to find the sum of the series, okay? So let's go with the first one. Summation n goes from 2 to infinity, e to the n plus 1 over pi to the n. Hopefully you can realize that you can write this as a geometric series. So we go through the motions of algebra. E to n plus 1 we can write as e times e to the n. Okay? This e I can move out of the summation. And this I can combine into 1 power, e over pi to the n. Okay? We know this is convergent because this is approximately, if I write out the approximate decimal value of e and pi. E is like 2.7, pi is 3.14. This is the common ratio, which is clearly less than 1, so it's going to converge. Okay? That's the original guy. Does it absolutely converge? It does, because the absolute value of this guy is the same thing. Everything's positive. So if you take the absolute value, it's still positive, right? So it absolutely converges because the absolute value, if it's absolute value, it converges. That's honestly what you just need to check for absolute convergence. Only if it's that absolute value doesn't converge, then we have to check for conditional convergence. So just to clarify on that. But to find the actual sum, well, we know how to find the sum of a geometric series. So don't forget this e though. I almost forgot it. You need the e there still. The sum of a geometric series is the first term. So the first term is when n equals 2. So e over pi squared over 1 minus the common ratio. Okay? If you want to simplify, honestly, I would accept this as the final answer. You can simplify to e cubed over pi squared minus e times pi. Okay? Part B, this one, summation as n goes from 0 to infinity, minus 1 to the n over times 1 over n ln n. How do you, in the world, would you start from n as 0? Undefined. How in the world would you start even from n as 1? ln of 1 is 0. Undefined. This is a bad question. You can't start the series from 0. So it's not convergent at all. Okay? So if this is the actual trick to this question, it's not convergent at all. Let's assume that the teacher actually wanted to start it from n is 2. Okay? It can only work from n is 2 and onward. It doesn't even work at n is 1 as I explained. Okay? So let's assume that it's from n is 2. Okay? So if we take the absolute value of this, the changing sign would go away, right? Now we do the integral test, because this, you can see a clear substitution that you can do. We can do the integral test to determine the convergence of the series, the absolute value, okay? So integral from 2 to infinity, 1 over n ln n dn, as I said, this is obvious substitution. That's why I chose the integral test. U is ln of n, du is 1 over n dn. You go through the motion of evaluating this improper integral. This is just log, right? And then log of infinity. I never used the limit notation like in the other problem. I did the way most people write it. It's divergent by the integral test. By the way, to use the integral test, you have to show that it's decreasing, which I did over here actually. So let's jump to over here now. It's not absolutely convergent, but it could be conditionally convergent if this original guy converges. Okay? How do we check if this guy converges? Well, it's alternating series, so maybe let's use the alternating series test. So what if we take the limit as n goes to infinity of this guy without the changing sign? It's clearly 0. Okay? But to use the alternating series test, we have to make sure that this guy is decreasing. So I kind of did this first, and then I did that again. But anyway, to check it's decreasing, we can differentiate. If the derivative is negative, then that means it's decreasing. So here, I change this to n ln n all to the -1 part. So I first used the power rule, and then the chain rule, which I needed product rule as well. Okay? Simplify, you get here, clearly, there's a minus sign there, okay? It's going to be negative for n is greater than like e, for example. Okay? Which, again, if this started from 2, it's totally fine that it's decreasing starting from after 2, because e is like 2 point something. As long as it's decreasing to infinity, we're good. If it starts increasing a little bit at first, who cares? It's a finite number of terms. Okay, so since it's decreasing and the limit is 0, it converges by the alternating series test. Okay, to recap over here once more, we checked for absolute convergence, so we need to find the absolute value of this guy, which is that, and I used the integral test, which the condition is if it's decreasing, positive and decreasing, I showed it's decreasing over here, and for sure it's positive, because log is positive when n is greater than 2, and, sorry, n is greater than e. So maybe let's start from, so yeah, n is greater than e, that's fine, as I said. If it's a finite number of terms, it's fine, similar to decreasing. If it's finite number of terms that's negative, totally fine. And it's positive and decreasing, and then the integral test showed that it diverges, so then the series diverges as well. Since the absolute value diverged, but the original converged, we call this conditionally convergent. Hopefully that made sense. Again, if the teacher actually meant to start from n is 0, this is a bad question because you can't start it from 0. So actually, it's an easy question. It's not convergent at all. How in the world do you divide by 0? You can't. Okay. This one, to check for absolute convergence, you could directly use the ratio test. And this was a good candidate, or factorials. Whenever you see a factorial, it's probably a good idea to use the ratio test anyway to check for convergence. And the ratio test directly checks for absolute convergence. So we go through the motions of the ratio test. A sub n plus 1 divided by a sub n, meaning where there's n, replace it with n plus 1, and then multiply by the reciprocal. Don't have the alternating sign because we're in absolute values, so it would go away anyway. Okay? So we go through the motion simplifying. 2019 to the n plus 1 divided by 2019. That's just 2019 to the first power. n plus 1 factorial is on top still. n plus 2 factorial is n plus 2 times n plus 1 factorial. Okay? These n plus 1 factorials cancel. Now we take this limit is 0, which is less than 1, so it absolutely converges by the ratio test. Okay? Since absolute convergence, you're technically supposed to find the sum. Honestly, I have no idea how to find the sum of this. I never learned it, so if you're on the test and you're crunched on time, skip that portion. This, honestly, probably would give you at least half the points already. Okay, if you actually needed to find the sum for this, then maybe there's a way to do it. I didn't spend the time to figure it out, honestly. Okay. This is the last page now, integrals. Evaluate this integral. This one looks kind of intimidating, but technically, even without simplifying like I did, you could evaluate this because we know the rule to evaluate sine squared, not sine squared, sine to the 6x, you have to use the half angle identity multiple times. Here as well, you have to use the half angle identity multiple times as well. So it's doable, but it's going to be tedious. So I honestly did not want to do that, so I thought maybe I can simplify something. So what if I factor out sine to the 4th from both terms? Okay, so I would have sine squared plus cosine squared left on the inside. This is just 1. My life's easier now. Sine to the 4th x dx. Here, I don't have to use the half angle identity as many times as I would have had to if I directly integrated sine to the sixth. Okay, sine to the fourth, we use the half angle identity because this is sine squared squared. So this is sine squared with the half angle identity and then another square to make it to the fourth power. Okay, I expand this out, so distribute this half to this squared to the half, that's 1/4. Distribute this squared to the half, I expanded it. So 1 minus 2 cosine 2x plus cosine squared 2x. Okay. Now, what do I do next? I evaluate these two first. Okay. So integral of 1 is just x, but we have the 1/4 there. Integral of 2 cosine 2x is 2 divided by 2 sine of 2x, and then with a 1/4 there. So that's what I said there. I wrote there, and then this 1/4 we put it to there, and then we use the half angle identity again. So I did a lot of steps in this one line over here. Hopefully that makes sense over there. So these two I directly integrated or found the antiderivative already, and this one I used the half angle identity again, but you have to keep track of this 1/4. Distribute to every term. Okay, this 2 and 1/4 I probably combined over there. All right, now here, this is the 1/8, right? We can integrate. This is simple. So it would be 1/8 x plus 1/8 and then 1/4 sine of 4x plus c, okay? And now you just got to combine some like terms. I combined that to that, and then 1/8 x and then 1/4 x you can combine to 3/8 x, and that's your answer. Okay, so not too bad for this one. This one's a piece of cake, honestly. If you remember the integral formula for arctangent x, the general formula, you can directly go to here. 1/4 arctan x over 4 plus c, you're done in 2 seconds right there. Maybe 3 seconds, because it maybe takes longer than 2 seconds to write this. Okay? And you can even quickly check if you differentiate this, you get back exactly that. Okay? Let's say you don't remember the formula for arctangent, the general formula. Okay? How would you do this though? Then, honestly, you could do a trig sub. If you really wanted, that's totally fine. But I didn't do that here. Here's the algebraic hack that you do. Because you know that arctangent is 1 over 1 plus x squared. The integral of 1 over 1 plus x squared is arctangent. So you're going to make it look like that. How do we do that? Well, this needs to be a 1, right? So what if I factor out 16? Okay, so I would get this over here. This I can write as one quantity squared. X squared over 16 is the same thing as x over 4 squared. Now I make the substitution. U is x over 4, du is 1 over 4 dx. Substitute. Dx is 4 du, so that's why it's 4 over 16, which is 1/4. Okay, and then this is my u, so u squared plus 1. Okay, this is arctangent now. Okay, and then back substitute u as x over 4. Exact same thing. This is how you can do it algebraically. If you recognize that it looks like arctangent, but it's not quite there. Again, you could have used trig sub here as well if you really wanted to. I didn't do that here. Okay, last one. This one's actually also a piece of cake. You just do a substitution. This is a very obvious one. Hopefully you can see it at this point. U is 4 minus x squared. Du is minus 2x dx. We substitute x dx is du over minus 2, so minus half du. And the square root term is square root of u, because this is u. Okay? Use the power rule. It'll be minus half times 2 square root of u plus c. Simplify and back substitute. That's your answer. Don't forget your plus c, honestly. Okay? And that's it for this exam. So hopefully you saw that this was, if you see my other UCLA practice problem set, or the study guide if I remember correctly, those problems were much easier than the ones here. There were some easy ones, like these two were a piece of cake. Some harder ones, like, which one was harder? Like maybe this one was more challenging. It's not that bad though, if you realize that you had to use that. These were a piece of cake, honestly. This one might have been a little more challenging, more intermediate per se, but not bad at all. You just have to do long division first. But the point is, hopefully this was a good practice problem set if you were looking for one. And if you've also found this online, hopefully my worked out solution could help. Again, I can't guarantee that I got all my answers right, so do double check me. and leave a comment if I got something wrong. Okay, but hopefully this helped. And as always, I will end with please like and subscribe if you found this helpful in any way, and please do share this video too if you're in UCLA and you found this helpful. You can share it with your other classmates and friends to help my channel out.